Yeah, so in this video, I'm just gonna basically focus on integration problems whereby you need to do a long division on that. So suppose that you have a polynomial that's given by something like this, and it can progress like this. And here I'm just gonna have a to x to the k plus b to x to the k minus 1 and plus like that. So now here you have two polynomials. This polynomial in the numerator is a polynomial of degree n, and from the denominator you realize that you have a polynomial of degree k. Now suppose that n is greater than k. If n is greater than k, that's where you have to work out on a long division of that. So you need to keep that in mind, that if the degree of the numerator is greater than the degree of the denominator, then you can use a long division on that. Now I'm just gonna do one problem here. Suppose you have 2x to the third plus 3x squared plus 5x plus 2, and then you divide that by let's say it's just x squared plus x plus 1. Yeah, let's say it's something like this. Now notice that this is degree 3. The numerator is just degree 3, and the numerator here is just degree 2. So you need to keep that in mind. Then it satisfies this condition, then we can use a long division to work on that. So now I'm just going to do that on the side. So now you have 2x to the third plus 3x squared plus 5x plus 2. And we're dividing that by x squared plus x plus 1. So now what I'm going to do is I'm going to take this number and then divide it by x squared. So 2x to the third divided by x squared, that's just going to be 2x. And now you say this 2x, and now you multiply by x squared, then you're just going to have 2x to the third. And then from then you can just say that this 2x, you then multiply it by x, and then you'll get 2x squared. And then you say this 2x, and then you multiply it by 1, then you'll have positive 2x. Now what you do is that you take you subtract both terms here. You take this one and then you subtract that from that, and then that means that you'll have 2x cubed minus 2x cubed, which is 0, and then 3x squared minus 2x squared, which is just going to give you x squared, and 5x minus 2x, that's just going to give you 3x. And then since 2 does not have a like term here, you're just going to copy it as it is. And then now you say x squared divided by x squared, then that's just going to give you 1, and then you just repeat the same process again. Then you say 1 by x squared, so that's just going to give you x squared, and then you say 1 by x, that's just going to give you x, and then you say 1 by 1, that's just going to give you 1, and then you just take the difference of that x squared minus x squared, 0, 3x minus x, that's just going to be 2x, and 2 minus 1, that's just going to be 1. So now notice that the degree of this is greater than the degree of that, so that this is just going to be the remainder of that. So how you rewrite this, you're going to say that this is the same as the integral of, now you copy this term as it is, 2x plus 1. So you're just going to have 2x plus 1 plus, now you take the remainder term here, which is just 2x plus 1, and always the remainder term you divide it by what you were dividing by. So it's just going to be x squared plus x plus 1 dx. Now notice how I reduced the degree of the numerator, and then I just split that. Now it will be simple to integrate that, because for now we realize that we can split the integral into the integral of 2x dx plus the integral of 1 dx, which is just going to be integral dx, plus the integral of 2x plus 1 over x squared plus x plus 1 dx. So now the integral of 2x, you can work that out, it's going to be x squared, and integral dx is just going to be x. It's just going to be x, and now you can use u substitution on that one. Let u equals x squared plus x plus 1, and then from then you can be able to integrate this one, which if you integrate correctly, you're going to get that this is the same as the integral of, there's no need for absolute value since this is always greater than 0, the integral of x squared plus x plus 1. The integral of 2x plus 1 over x squared plus x plus 1, it's just going to be ln x squared plus x plus 1, and then when you're done integrating, you can just add a constant on that. So that's how you can use a long division method to integrate that. And from now in a similar case, you can be able to work this integral out. X to the 6th minus 1 divided by x to the third minus 1 dx. Similarly, you can be able to work this integral out using long division. So you're just going to say that you have x to the 6th minus 1, and you're dividing that by x to the 3rd minus 1. So now notice that x to the 6th divided by x to the 3rd is just going to give you x to the 3rd. Now you say x to the 3rd times x to the 3rd, you're going to get x to the 6th. And now you'll say x to the 3rd multiplied by minus 1, you're just going to have minus x to the 3rd. Now you're just going to take x to the 6th minus x to the 6th, which gives you 0. And minus x cubed doesn't have a like term, so you'll say 0 minus into this one, which you're going to have positive x to the 3rd. And now notice that you're still going to have this minus 1 here. You're just going to copy it here. And then you'll say x to the 3rd divided by x to the 3rd, then you're going to have 1. And then you'll say 1 times x to the 3rd, you're going to have x to the 3rd. And you say 1 times minus 1, which you're going to have minus 1. And then you have no remainder. So what this means is that this integral is the same as you copy this term, x to the 3rd plus 1. So there's no remainder, it's 0. So you have 0 over x to the 3rd minus 1. So this term is not there. So there's no remainder when you divide this by this. So you can use long division to quickly evaluate the integrals. And for this one, you're just going to have x to the 4th over 4 plus x plus constant when you evaluate this integral out. So that's how you can basically use long division to evaluate integrals. So it's basically not that complicated really. I mean, similarly, you can work on other examples, including suppose you have x squared plus x plus 1 divided by x plus 1 dx. So you can easily use long division to evaluate this integral out. It's not that complicated really, as long as you get the whole procedure of that. So now what I'm going to do is I'm going to show you how you reduce that x plus 1 and make sure you're practicing this with me so you can get the hang of it. So you'll say x squared divided by x, then you'll have x, and then you'll say x times x, so you'll have x squared, and then you'll say x times 1, then you'll have x. Then you're just gonna subtract, then you'll just basically have x squared minus x squared is 0, and then x minus x is 0, then you only remain with 1, and then you have something like this. And now basically that means that you can rewrite this integral as the integral of, you copy this term, which is just x, and then you add the remainder is 1, and always the remainder you divide it by this one, which is just going to be x plus 1 dx. So now you have something like this. You can easily evaluate it, and then you'll have the integral of x dx plus the integral of 1 over x plus 1 dx. Sorry about this. The integral of 1 over x plus 1 dx. So now this means that you're just gonna have to integrate this. You can do it directly, then, which will just be x squared over 2 plus the integral of this. You can use substitution, then you just have lean the absolute value of x plus 1. Then you add a constant, then you're done. It's basically this simple really. So you can basically integrate almost all polynomials because it's basically simple really. You can just integrate that out using long division to simplify it, and then you should be able to get the hang of it. So suppose now you're integrating something like this. Can you pause the video and see if you can be able to integrate this? Please try to integrate this so you can see if you're struggling or not. So you can use long division on that. So the thing about long division is that if you cannot factorize, it's easier to use long division because it doesn't need you to know how to factorize. But other people prefer to factorize this. Yes, you can factor this, but then if you cannot factorize, then you can use the long division method. It won't interfere with your answer. Whether you solve this using factorization or by long division, we're still going to arrive to the same answer. At least if our math is correct, then we should be able to arrive to the same answer. Then you'll have x plus 1 as a numerator, as a denominator, and then x cubed plus 1 is the numerator there. Then you say x cubed divided by x, you'll have x squared, and then you'll say x squared times x, you'll have x cubed, and then you'll say x squared times 1, which you're going to have x squared, and then you say x cubed minus x cubed, which is 0, and then x squared doesn't have a like term, then you're just going to say 0 minus this, so you're just going to have minus x squared, but then you will take 1 down there, so you have minus x squared plus 1. Then now you say minus x squared divided by x, which is just going to have minus x, and then you say minus x times x, which you're just going to have minus x squared, and you say minus x times 1, so you're just going to have minus x. Now you'll say minus x squared, which is 0. Minus x squared minus into negative x squared, which is going to give you 0. And then you'll have minus x with no like term. So you have 0 minus into negative x, which you're just going to have positive x. And then you'll say, since 1 does not have a like term here, you're just going to copy it as it is. Then you say x divided by x, which is just going to give you 1. And then you'll say 1 times x, which is just going to give you x. And 1 times 1, which is just going to give you 1. And x minus x is 0. 1 minus 1 is 0. So there's no remainder. It's how we worked it out. If there's no remainder, there's no need to rewrite that other term. So you're just going to basically have to rewrite this integral as the same as the integral of x squared minus x plus 1. And there's no additional remainder term because there's no remainder here. Since there's no remainder there, then this is the same as that. So yeah, so that's how you can use long division to evaluate integrals. Thanks for watching. Don't forget to share and subscribe.